So today I'm going to talk about the GIT moduli space of the Pfaffian representations of cubic threefolds. So I will start with a brief introduction on Pfaffian representation of cubic hypersurfaces. Then I will illustrate the main motivation behind our interest in the subject, that is the link that exists between Pfaffian representation of cubic threefolds and instanton bundles on cubic threefolds. Then I will present some properties of the moduli space of Pfaffian representation. That is a moduli space that can be obtained by means of geometric invariant theory. And finally, we will see how certain points in our moduli space that does not define proper Pfaffian representation are still connected with some sheets in the moduli space of instanton on a cubic threefold. So to begin with, we consider the following objects. So we take a complex vector space V of dimension n+1, a complex vector space W6 of dimension 6, a form of degree 3 on V, and we consider X the cubic hypersurface defined by the following form. And we ask the following question. So is it possible to find a skew symmetric matrix of size 6 whose entries are linear forms and whose Pfaffian is exactly the polynomial defining the hypersurface? So is it possible to find a so-called Pfaffian representation of our cubic? So let's see a little bit what is known about Pfaffian representation of cubic hypersurfaces. So the existence of this representation is rather a classical subject in algebraic geometry. The first result concerning the existence of Pfaffian representation of plane cubics are, I think, the first one came already from Cayley. I was not able to find an exact references for the first one that proved the existence of Pfaffian representation of plane cubics. But by the way, it is known, classically known, that plane cubic curves are always Pfaffian. When we pass to Pfaffian representation of cubic surfaces, we have that in 2002, Fanny and Mezzetti proved that every cubic surface is Pfaffian. And later, Tanturi in 2015 provided a constructive proof of the existence of cubic surfaces. And concerning Pfaffian representation of cubic threefolds, the first results were obtained by Adler and Ramanan in 1996. They proved that general cubic threefold is Pfaffian. And how did they do this? So they consider the Klein cubic. They constructed explicitly a Pfaffian representation of the Klein cubic, and they showed that the differential of the Pfaffian map, so the map that sends a matrix to its Pfaffian, is surjective at the matrix corresponding to the Pfaffian of the Klein cubic. Later, Boville, using results from Markushevich and Tikhomirov, proved that every smooth cubic threefold is indeed Pfaffian. So let's try to see what happens if we consider singular cubic. So if we move to singular cubics, then we can prove, this was one of the main subjects of my PhD thesis, we can prove that every cubic threefold admits Pfaffian representation. So to do this, we will distinguish three families of cubic hypersurfaces of cubic threefolds. So we consider the cubic threefold that presents triple points, but then the existence of Pfaffian representation is deduced by the existence of Pfaffian representation of cubic surfaces. For a cubic that has singularities in codimension 1 or 0, so non-normal cubic, we are able to write down explicitly by hand a matrix of linear forms whose Pfaffian define the cubic. And the most interesting case is the case of normal cubic that present at most double points. And in this case, we are able to construct Pfaffian representation starting from the so-called normal elliptic quintic arithmetical Gorenstein. So curve C on X will be called a normal elliptic quintic arithmetical Gorenstein if this arithmetical Gorenstein, so its ring of homogeneous coordinate is a Gorenstein ring. It has this Hilbert polynomial. It is non-degenerate in P4. And the space of global section of the structure sheaf is exactly equal to C. So we have the following implication. Whenever a cubic triple contains a curve of such a kind, then it is Pfaffian. It is rather interesting to study how to construct Pfaffian representation starting from elliptic quintics, because in this context, we can understand how many geometric futures of cubic triples can be translated using the language of matrices of linear forms. So, for example, let's see how we can construct explicitly a Pfaffian representation from an elliptic quintic. If we have an elliptic quintic on the cubic X, then we can take its resolution in P4, and we obtain a complex of this form, where this differential is given by a skew symmetric matrix of size 5, whose entries are linear forms. So our curve will be defined by the intersection of 5 quadrics that are given by the principal Pfaffian of these metrics. Okay, so we have the quintic elliptic skew symmetric matrix of size 5. The principal minors are the quadrics defining the curve. But if the curve is contained in the cubic, then we can find linear forms such that we can write the polynomial defining the cubic in the following form. And then it is enough to correlate the matrix associated to the curve in order to obtain a Pfaffian representation of the cubic X. So here, in general, the structure of the resolution of the curve C is described by a well-known theorem by Eisenbud and Buschbaum. That is a structure theorem for high-tree Gorenstein ideals. But in our case, we deal with really, really well-behaved elliptic quintics. So in particular, all the elliptic quintics from which we construct Pfaffian representation of cubic triples are contained in cubic scroll. And if this is the case, it's rather easy to write down explicitly the matrix MC. So I would like to give an example of how this is done. Okay, so let's see. Okay. So we consider a cubic scroll, sigma, i.e. right, its Picard. So the generator of its Picard will be named D and F. So F will be the class of line in the ruling, and D the class of the directrix. So the cubic scroll sigma admits a determinantal representation. So we can find a matrix M sigma of linear forms of this kind. Okay, so from this we can construct a skew symmetric matrix of size 5. So usually I write better with the tablet, but now I'm nervous. The result is quite piteous. So anyway, here we have a skew symmetric matrix of size 6. So the scroll will be the locus where the matrix M sigma has rank 1. And we can see that here we have two tuples of linear forms that will define the generators of the pencil of lines in the rulings. So I will call them L5 and this L4. Okay. So let's suppose now that C is an elliptic quintic in our scroll. Then C must be linear equivalent to the anti-canonical divisor, and this belongs to this class. Okay, so the curve C is determined by the base locus of a space of quadrics that has dimension 5. We already have a three-dimensional space of quadrics that contains the curve C, that are simply the quadrics defining the scrolls. In other words, that are the minors of the matrix M sigma. So we'll still need a two-dimensional space of quadrics that contains the curve C. But then this is just the space H0 or sigma to H minus C. And this is exactly this vector space. And it has dimension 2 because it is parameterized by the directrix of the scroll. So this will be generated by a pair of quadrics that I call Q4 and Q5, where Qj is a quadrix that will intersect the scroll along a sextic of the form G plus Lj. So we have a pencil of sextic that contains the quintic. These are all of the form quintic plus line in the ruling. So now we take the two lines, these two lines of the ruling, so L5 and L4. We will determine two quadrics, Q4 and Q5. And so in particular, we will be able to find linear form H1, H2, H3, such that Qj might be written as sum over I of Hi, L, Ij. But this means that we can find a representation of the curve of this form. So here we will have M sigma 0 minus M sigma t. And here we have our three forms. And so here is how we can write down explicitly by hand representation of the curves without applying the theorem of Buchbinder and Heisenberg. So let's now come back to the presentation. Okay. So we can now try to understand why we are interested in the study of Pfaffian representation. So this is due to the fact that on a cubic threefold, a Pfaffian representation corresponds to a so-called rank 2 Ulrich sheaf that is moreover skew symmetric. This means that it is a sheaf supported on X that has rank 2 on X and whose resolution in P form is a linear complex that has two terms and whose wholly non-vanishing differential is given exactly by a skew symmetric matrix whose entries are linear forms. So we can take this characterization by means of resolution as a definition for a rank 2 skew symmetric Ulrich sheaf on a cubic hypersurface. So from the shape of the resolution, we can deduce that the shape of the resolution might be rephrased by the vanishing of these cohomology groups, so that in particular we see that our sheaf does not have intermediate cohomology, so it will be a sheaf arithmetically Cohen-Macaulay, and we can also observe that it's whenever the sheaf is locally free, it is always possible to make its resolution in P4 self-dual. So we can always find a way to make this differential skew symmetric. We have an action of the group GL6 on the resolution, and we can observe that whenever we have two Pfaffian representation of the same cubic hypersurface, they will define the same Ulrich sheaf if and only if they lies in the same GL6 orbit. So let's now try to understand what happens when we construct Pfaffian representation starting from elliptic quinting. So how to have an interpretation of elliptic quintics from the point of view of the behavior of sheaves. So for the moment, we consider locally free Ulrich sheaves. So we consider an Ulrich bundle of rank 2 on a cubic hypersurface. Then from the resolution, we can see that the space of global section of the bundle is exactly W star. So a global section is just defines a hyperplane in the space W6. The zero locus of this global section will be the locus of points in P4 where this matrix that will be a skew symmetric matrix that will have rank 4 as kernel contained in this hyperplane WS. So we see from this that this locus will be contained in the support of the Ulrich sheaves, because this means that the form Mx must have rank 4. And in particular, we have that this locus is exactly an elliptic quintic that is arithmetically Gorenstein. And the matrix, the skew symmetric matrix of linear forms defining it will be simply the matrix obtained restricting each form to the hyperplane WS. If now we start from an elliptic quintic on on our cubic hypersurface, and we take a matrix, a skew-symmetric matrix of linear forms, whose principal Pfaffian defines the ideal of the curve. Then we can observe that we have the following. So whenever we take linear forms that allows us to write the polynomial defining the cubic in the following form, then we are defining, we saw this in the past section, we are defining a Pfaffian representation of the cubic. So we are defining Hurwicz sheaf on the cubic plus a global section of the sheaf that will vanish exactly on the curve. We also observe that these 5 tuple of linear forms might not be uniquely determined, but it varies in a linear space of 5 tuple of linear forms, and every other 5 tuples in this linear space will gives rise to the same Hurwicz sheaf. So will give rise to Pfaffian representation lying in the same GL6 orbit. If now we suppose that our cubic is smooth, we have that whenever we twist our Hurwicz bundle, we will get a so-called instanton bundle of minimal topological charge. So we will get a stable rank 2 bundle that has 0 first Chern class, the vanishing of this group of cohomology, and the charge is just the second Chern class. And conversely, whenever we start from an instanton on the cubic, we twist it by 1, we will get a Hurwicz bundle. Bundle always implies skew-symmetric. So it means that on a smooth cubic threefold, instanton bundles or Hurwicz bundles correspond to Pfaffian representation. We can use this correspondence to construct a new compactification of the moduli space of instanton on the cubic, different from the standard Gieseker-Maruyama one. And the first step to do this is to construct a moduli space of all the Pfaffian representation of cubic threefolds. So we can construct this space as the GI quotient of the locus of semi-stable matrices of linear forms. We take the quotient by the action of the group GL6. And we just get an irreducible projective scheme that has dimension 39. If we take then M, that is the component of the moduli space of sheaf in P form, whose generic point is an instanton supported on a smooth cubic, then we get a commutative diagram of this kind, where this map is birational. So it's a birational map which is between these two spaces of dimension 39. And whenever we pick a smooth cubic, the fiber of PF bar will be a 5-dimensional compact scheme that will be a compactification of the moduli space of instantons. So we finally come to the actual study of our GIT moduli space. In order to understand how this guy behaves, the first thing is to understand which kind of points we find in this moduli space. So we need to establish a stability criterion. So this is how the stability criterion looks like. So it characterizes the forms that the matrices might have. So as it is quite difficult to understand visually the stability from here, it is possible to reformulate the criterion in this way. That is a little much easier to visualize immediately. So roughly speaking, unstable, that means not semi-stable matrix can be reduced to one of the following forms. So if ever we are able to find coordinates on W6 that allows to write the matrix in having one of these blocks of 0, then we will have an unstable point, so points in the null cone. Similarly, all the semi-stable points, so either strictly semi-stable or stable, for a suitable choice of coordinates on W6, might be reduced to one of these forms. So from the criterion, we can deduce immediately that whenever we have a matrix of linear forms whose determinant is non-zero, so whose Pfaffian is not zero, then it is automatically semi-stable. So all Pfaffian representation of cubics will give us points in the moduli space. One of the first questions in GIT theory is if either we have strictly semi-stable points, so all the semi-stable points are stable, or we have also strictly semi-stable ones. So the answer is positive, and we have strictly semi-stable representation, and an example is provided by the determinantal cubics. So if we take a cubic that is defined by the determinant of 3 times 3 matrix of linear forms, then it will be automatically Pfaffian, because we are able to write down immediately metrically forms. And if we look at the criterion, we see that we have these blocks of 0 that will not allow our matrix, our representation, to be stable. So this is an example of strictly semi-stable representation. What we can prove is that actually, if ever a cubic admits strictly semi-stable representation, then it must be determinantal. And among all the strictly semi-stable representation, all that are polystable, so all those that has closed orbits are actually those that are induced by the determinantal one. So by star, I indicate a representation of that has this block structure. So determinantal, and the 2 0 blocks. If now we move to the language of sheaves, let's try to understand what we are doing. So for the moment, we suppose for simplicity that the cubic is irreducible. We take an irreducible determinantal cubic. Then we argue in a way that is completely equivalent to the one concerning Pfaffian representation. So we consider the complex of vector bundles on P4 determined by the matrix of linear forms n. We take its cokernel. This time we will get rank 1 Ulrich sheaf. And if we take the polystable Pfaffian representation of the form star, then its cokernel will be an Ulrich sheaf of this form. So we will get a polystable sheaf, because it is a direct sum of stable sheaves. And if now we see, we try to understand which kind of semi-stable points has orbits whose closure contain the polystable ones, we have that all these semi-stable points are of this form. So we take the polystable representation and we add blocks of linear forms. The cokernel of these matrices, so the corresponding Ulrich sheaf, will be exactly sheaves belonging to the same as equivalent class of the Ulrich sheaf associated to the polystable representation, because each of these blocks that we are adding will define a non-trivial extension in this class. So the polystable one define a trivial extension, direct sum of two Ulrich sheaves, so a polystable sheaf, polystable matrix, polystable sheaf. Every matrix whose orbit, whose closure of the orbit contains the polystable one, define a non-trivial extension. Hence, another sheaf that will be that will define the same sheaf in the modular space of sheaf, the same point in the modular space of sheaf. So I would like to, again, to use for a moment my tablet to continue with the example. Because we can, it is natural to ask what happens then if we construct Pfaffian representation of a determinantal cubic starting from elliptic quintics that are contained in a cubic scrolled contained in the cubic, because a determinantal cubic will be a cubic threefold that contains a cubic scroll. So what happens if we construct Pfaffian representation from elliptic quintics on these scrolls? So let's take determinantal cubic. So we have a determinantal representation. 1, 4, 5, 6. So here I have a block of 0. So I call this matrix, this is our matrix N. We will have minus NT transpose. Okay, so how can we see all the cubic scroll or possible degeneration of cubic scroll that will lead to determinantal representation of X? Well, it is enough to erase one line or a column in the block N. So if, for example, we erase this column, we have that this submatrix will define a scroll sigma. So I keep the notation that I adopted before. And so if now we take quintic elliptic in this scroll sigma, we do the trick that we applied before. So we can get matrix MC of the form which one? 0, 0. Here we will have M sigma. So if now we had the column, the sixth column, we see that we will get a matrix M prime, another Pfaffian representation of the cubic M prime. It will be just M sigma, here L1, 6, L2, 6, L3, 6. Here a block of 0. Here we have our free forms. And here, so this is just N. So these blocks of 0 tells us that the matrix can't be stable. And from the proposition that we proved above, we have that this is not polystable. Not polystable, so it's strictly semi-stable. And we will have that the GL6 orbit of N is contained in the closure of the GL6 orbit of this matrix M prime. So these matrices will define the same point in the modular space. Okay. So example of irreducible determinantal cubic threefolds are the following. So we have a general determinantal cubic threefold. Is a cubic that presents 6 double points in a general position. We then have the possible degeneration of this situation is the second variety of a rational quatic. And we can easily get a determinantal representation of these threefolds starting from the determinantal representation of the quatic. So here we see, here we'll have all the scrolls that are contained in our cubic. So whenever we have a strictly semi-stable representation, then we have a determinantal cubic. So if the cubic is not determinantal, then we can prove the following. So that every Pfaffian representation will determine a stable Hurwicz sheaf. So the fact that we don't have rank 1 Hurwicz sheaf will imply the stability of the rank 2 Hurwicz sheaves on the cubic. We will deduce the fact that this stabilizer of the Pfaffian representation will be trivial. So that in particular, if we look at the local structure of the quotient in a neighborhood of this representation, we will have that the quotient looks like a principal bundle with this structure group. Okay. So in the last part of the talk, I would like to illustrate how we can have actually have points in the moduli space of Pfaffian representation that are still connected with the sheaves in the moduli space of instanton. So we go back for a moment at the moduli space of instanton on a smooth cubic threefold, and we consider is Gieseker-Maruyama compactification. So this moduli space had been studied by Druel, who proved in 2000 that this scheme is smooth of dimension 5. And Druel also gave a complete description of the boundary of this moduli space. So he proved that in this boundary, we have two families of sheaves that are non-locally free, whose singular locus is a curve. And in particular, we have that each of these sheaves is obtained by elementary transformation from a one-dimensional sheaf that is either half of the zeta characteristic of a conic on the threefold, or the direct sum of the structure sheaf of two lines on the cubic. So when I say that it is obtained by elementary transformation, it means that the sheaf will fit in an exact sequence of this form. So we can observe that the support of the sheaf T will be exactly the locus when the sheaf F is not locally free. And if we now pay attention to the sheaf T, we can observe that it is incredibly well behaved. And if we do exactly as we have done for Hurwicz sheaves, and we take its resolution in P4, we can see that we still get a self-dual complex, a self-dual linear complex. So we get a complex of length 3, whose differential are matrices of linear forms. And here, this differential will be given by a skew symmetric matrices that this time will have Pfaffian equal to 0 and will be such that the locus of points where the matrix as rank equal to 2 will be exactly the support of our sheaf. So we get other families of it means that when we study the boundary of the moduli space of instanton, we produce other matrices, skew-symmetric matrices of linear forms. So let's try to check if they are stable. And what is remarkable is that indeed these matrices are stable. So we have stable points that does not define cubics. So we saw that we have an implication, the fact that a matrix of linear forms as non-zero Pfaffian implies the semi-stability. So this example shows that the converse is not true. So we can have matrices with zero Pfaffian that are even stable. If we are able to classify all the stable matrices having zero Pfaffian, and we obtain 3 stable orbits. So these are all the possible stable matrices with zero Pfaffian. And in each case, we have that the locus of points in P4 when the rank is strictly less than 4 is respectively a conic, a pair of disjoint lines, and singular conics consisting of 2 lines intersecting. If then we look at the locus of matrices that has rank less than or equal to 4, so for the moment we are able to prove the following. So we are able to locate 2 smooth irreducible components of this locus that are exactly orbits by the action of GL6 times GL5 of matrices associated to conics and matrices associated to pairs of skew lines. So when we take the quotient of these components, we will get 2 irreducible schemes of dimension 11 and 12. And moreover, we have that in the intersection of these 2 components, we will have all the points associated to singular conics. So all the metrics associated to intersecting lines. We can prove that the stabilizer of a matrix associated to a smooth conic is trivial. This implies the smoothness of the GIT moduli space in the point, of course, also of the component Z prime in the locus of matrices of rank less than or equal to 4. And so we have that both these quotients are principal bundles when we move in a neighborhood of our matrix. This also allows to study how to extend these rational maps in a neighborhood of a matrix associated to a conic. So we are able to extend this rational map to these components of dimension 11. And moreover, we have that this map behaves like a blow up with center in Z prime. Unfortunately, things get quite more difficult when we move to matrices associated to pair of lines, because in this case we don't have trivial stabilizer, but we have an involution. So this is just an involution that inverts the lines, and so it means that the quotient will be singular in this point. And so we won't have a principal bundle of structure group GLW6, but we will have this principal bundle quotiented by an involution. So we will have to solve some singularity in order to extend these rational maps. So in other words, what we are saying is that the stable points in the locus Z describes exactly those sheets that allows to obtain instanton sheets in the boundary of the moduli space of instanton sheaves. So these components describe the sheaves from which we get the boundary of the moduli space of instanton by elementary transformation. So again, we try to see what happens if we want to understand which are the strictly semi-stable points in the locus Z, and we can classify all of them. So once again, we have just three types of strictly semi-stable orbits, and we have a situation that is completely equivalent to the one of Pfaffian representation. So the only polystable one are those that comes from determinantal representation. So are just the matrices that have this block structure. So the determinantal part, and then the 2 0 blocks. In all these cases, we will have that the locus of points in P4, where the rank is strictly less than 4, will be a double line. Once again, we will have that the matrices will define linear complex in P4 of this form. This time, if we take the co-kernel of this differential, we will still get a sheaf of dimension 1 that will be supported on a double line, and that will be a so-called twofold extension of a line. So it will fit in a short exact sequence of this form. So whenever we take a polystable point, this sheaf will be exactly the direct sum of the structure sheaf of the line. And once again, exactly as it happens for Pfaffian representation, whenever we take a strictly semi-stable point, so a point with non-closed orbits, we will have that it will determine a non-trivial extension here. So it will define a sheaf that is S equivalent to the co-kernel of M, of the polystable matrices. So once again, we will get the same point in a moduli space of sheaves. So what we still need to understand is the following. So is it possible to give a geometric description of the two components that we obtain? So remember that we obtained a component of dimension 11, a component of dimension 12. So what I'm trying to understand, so for me, they should be somehow birational to the Hilbert scheme of conics and to a symmetric power of a Grassmannian, because these are components that parameterizes sheaves on conics, and we have dimension 11, that is the dimension of conics in P4, and a component that describes families of pair of disjoint lines. These components has dimension 12, so Grassmannian of lines in P4 has dimension 6. So somehow they parameterizes the support of these sheaves. So what we need to understand if these are actually isomorphies, just birational. So is it possible to give a concrete geometric description of these two components? So are these all the components in the quotient of the locus of matrices of generic rank less than or equal to 4, or do we have other components? And once we have done this, what can we say about the extension of the Pfaffian map to the locus Z? And what can we say then about the structure of the fiber? So about the compactification that we will get of the moduli space of instanton. And so that's all, more or less.